Hi there, welcome to this session on UVM Core Concepts Introduction. We have already gone through a UVM introduction session and we have established our strategy as to how we are going to go through this entire journey of learning the UVM. And our strategy is three-pronged, right? So first one, we would like to understand what are the core concepts that are involved in the UVM, and then the get a depth in the the common subset of base classes that are used across most of the projects. And the third one was that we wanted to master one of the working real life examples. So that's our three things that we want to learn in order to master the UVM. And this is the first part of that series, and the way we are going to do it is that we will first look at broadly what are the various core concepts involved. We have sort of introduced them as a part of introduction. We'll go one level deep into it. We are not go a complete depth, but we'll go one level deep, understand what's involved in terms of the core concepts, and little bit more, we'll know more about the core base classes, okay, and then how the overall test bench and the test flow works in UVM. And once we have done that, we will jump into a real life example, the bootstrapping, as we have done, and we will look at how to apply these things for a real thing and put together an entire system. And then we will go deep into each of these core concepts, and we will understand them in more detail. So that is our overall plan. So as a part of this session, we will peel one layer and we will go detail into what are little bit more about the core concepts, little bit more about the common subset of base classes as to what do they do, and then we will take it forward. So this is the agenda for the session. What we will do is we will little bit recollect what we have seen so far, so as to build the context, because UVM is the evolution, as we have seen the evolution of UVM as well. And in order to absorb such a long evolution, we need to at least shortly understand from our own experiences that we have had through this course as to how things have evolved. Like, we have done it at a very fast pace, but let's just recollect it a little bit, and so that we build the context. And that is important because when you know how things have come, how things were, and how things have progressed, you tend to better appreciate and understand why now UVM is doing it in certain ways, right? So that is the motivation. So because of that, we will just understand quickly like what sort of challenges we faced when we built the Verilog Testbench, what sort of challenges we have seen with the SystemVerilog Testbench. Challenges means not the understanding of concepts, but where are they lagging, right? So why did it move from Verilog to SystemVerilog, and where does the SystemVerilog Testbench stand, and what is it that it is not able to satisfy? We will understand that, and then we will understand the key concept, that the key essence of the UVM is standardization, and the standardization leading to reuse. So what exactly is reuse, right? So we'll understand that, and then we'll understand how does UVM accomplishes that reuse. And then we will just refresh some of it we have looked at in the introduction. So what does it mean to learn UVM? We will refresh that. This one we are refreshing so that this thing sticks in your mind, right? So that you always know what is the overall scope and what part of it you are learning in any given session. And then quickly, which SystemVerilog features are used in building UVM. Once we do that, we will have a good context to jump into the core concepts and the key base classes. So we will jump into that, and then we'll look at a little bit about like how the UVM test benches are created, and then we'll go into some key concepts like what's the test intent versus the environment, component versus objects. Some of these terms we have introduced. What is the base class hierarchy, and then whatever the core base classes, we will understand at least a quick formal definition for each one of them as to what they are intended to do. And then the main thing for this session, which is a key focus, the climax of this session, which comes towards the end, is we will understand the overall test flow. Right, so this is the key thing, that how do you connect a DUT, how do you configure it, then how do you generate the stimulus, how do you do the checks, and how do you do the coverage in UVM, right? So once you know this, then you have the sort of the background set to jump into a quick real life example, as we call bootstrapping. So you are ready to bootstrap into a real life project, right? And look at it as to how it is done. So this will set up the background for that. Okay, let's quickly reflect on to our verification experiences so far. So we started off with simple 4-bit counter DUT, and it just contained 16 states, and we could, give a 16 clock worth of stimulus and see how it counts through, and then maybe do few resets in the middle and see how the counter behaves. That is good enough for this DUT. However, if we get bored doing that, we will build a simple directed test case for a 4-bit counter DUT and look at it, so that we can repeat it again and again, and that would be more than sufficient for that DUT. But when we moved on to a 256-bit counter DUT, we understood we cannot apply the same philosophy and do the verification of it. We cannot sit and wait through all 2 raised to 256 minus 1 count. That was not practical. So we decided that we need to do some sort of a random verification, and we set ourselves some coverage criteria saying that, yeah, we'll divide this range of counts into several different ranges and check within each range, and then check some corner cases to make sure that we are able to verify the 256-bit counter DUT. That's when we convince ourselves that, yeah, we do need sort of a coverage driven constrained random verification approach to verify such a, like a relatively complex design. And then we moved on to SystemVerilog, and then we took a slightly more complex DUT, a synchronous FIFO DUT, and we applied, how we can structure coverage driven constrained random verification, and we were able to solve that the verification problem using SystemVerilog constructs, and we understood to some extent what benefits it provided. And at all these points, you might have gotten this question that, isn't this good enough, right? What's really lagging? After, at least even after seeing the system law, what exactly is lagging? So that is the question. Let's take it forward in next few slides and try to see what is that insufficiency that exists that we really need to fulfill. We'll just go through these series of steps quickly to make sure that we are clear that what was lagging in each step, and what is it that we were trying to accomplish whenever we moved forward from one language to another language, and now that we are trying to look at what is the verification methodology, what is it that has been lagging at each step, and what is it that we are really gaining by looking at these various things. So when we started off with Verilog Testbench, if we ask ourselves the question that what was lagging, Verilog of course was missing strong constructs to do the randomization, coverage and assertion. That doesn't mean these things were not done. Okay, that is a point I would like you guys to understand, that even when there was no construct to do randomization or coverage or assertion, people did this, right? So they created various using additional code, right? They wrote additional Verilog code, and they utilize these capabilities like interfacing with C++ using PLI, so that they can exploit the features. Some of these features that are present in the other languages, C++ for example is object oriented, so you can build part of object oriented Testbench using C++, interface it with using PLI. The people did such things, right? So that's what led to evolution. Otherwise, just like that, out of thin air, nobody gets a brilliant idea and they are able to come up with that. That's not how things happen, right? So people find out incrementally how they can make it better and prove that that's a better way to do it, and then that's when the language starts evolving. So if you look at it, we use like a $random based, we built some functions around that to generate the constraint, like a constrained random stimulus for our counter. And then we looked at that, when we were doing assertion session, for example, like a simple expression, like a concurrent timing expression, like a request followed by 1 to 3 clock cycles or sampling events of grant, how it required like 20 lines of multiple nested fork type of an arrangement in Verilog. So yes, so it is possible, right? So that is what it is. It's possible, and we can do functional coverage as well. Like we can print various values that we are simulating. A counter example, we could print with what count we are starting in the log files, and then write some post-processing scripts in Python or Perl to extract that information and then collate it across the tests that we have run and tell us whether those values that we are interested have taken place in the test bench. So it's not that it's impossible to do it, but then what happens is this additional code that we really write, any one line of extra code means one possibility of extra bug, right? And then the time, effort that's involved in maintaining such a code, right? The main the business reason that drives it is that when you build such code, it has no real value for the company, right? Because they are not really building a product out of it which has a differentiation. Everybody will do the same thing, and that doesn't reflect in terms of anything new to the customer of a particular chip, right? So like a customer would like to have more advanced features, higher speeds of operation, stuff like that. They don't care about how you wrote your Verilog code to build such a chip, right? So they don't care about it, and everybody is doing the same thing. And Verilog was sort of limited even with reuse, because the module task functions type of a thing, they help you build certain level of reuse, but because of their static nature, they are rigid, right? So that is the problem. And some of these problems, as we saw, people were solving. It's not that they were not solving, but that extra effort wasn't really translating into unique value for the businesses. And that's where people thought that, yeah, why does every company need to reinvent the same wheel? Let's put together these things that we are repeatedly doing. I am doing repeatedly randomization. Everybody is doing some sort of a functional coverage mechanisms by doing some print and all that hodgepodge schemes. And we are writing for assertions. We are repeating same set of code. So why not define them as constructs? Since many of the companies are repeatedly doing it, if we define it as language and build that as a construct, then everybody can do it in the same way. In the things that are not unique to that particular company, right? Every company, they are producing something unique, so they want to continue to do that. The common things, they don't want to do real innovation. So that's where these committees are formed, and then they implemented these features as constructs in the SystemVerilog, right? So that's how the things have evolved. Now, when we went to a SystemVerilog Testbench, that SystemVerilog provided us with the native constructs to do randomization. So there was a concept of constraints. We can put it in a class. We can call .randomize, and different type of procedural randomization were provided so that you can accomplish something simple in a simple way. And for a complex problem, you have a scalable object-oriented type of a system. Then functional coverage became part of the language. Now storing the values that are being created, and then putting it in a database, merging those database, creating coverage reports, all that became a part of a tool which is a standard EDA vendors can implement, and that tool can be now utilized across all chip vendors, right? So that is the motivation, right? So that is how, like, these companies fund some people and they form committees like Accelera type of committees where people sit and figure out how to solve common problems across industry through a language, and then give it to the EDA vendors, and then those vendors can go ahead and implement it. And as you go further in your career, you should probably look out for opportunities to sit in one of those committees and define what are the next set of language features that we would need to implement, right? So these complex verification problems that we had when we went to like a 256-bit counter, complex meaning that we had to put extra effort to do it, right? So those could be now done with ease when we do the same coverage driven constraint random verification, because I now have constructs natively available to me in the language, and the simulator is taking care of implementing them, so I don't have to take the headache, right? So, and then the class level object orientation provided us the ability to build the dynamic test benches. Dynamic test benches meaning that I can runtime configure how many number of some things I want, and then I can recreate whatever the test bench hierarchy that I would need. And this would not have been possible with Verilog, because Verilog we have to commit before even we do the compilation, we have to commit with the number of modules that needs to be instanced and how they need to be connected. Everything I need to commit right at the point of compilation, whereas that was not required with the SystemVerilog. So this is the sort of a step improvement, okay, in that particular direction compared to Verilog. But what was that was lagging when we did the SystemVerilog test bench? So what happens is that you don't generally build only one test bench, right? So in any bigger companies, they will have multiple IPs, and those IPs are being put together in subsystems. Subsystems are used to build socks, and they build multiple flavors of socks, right? And then they try to sell them. Now, when we have this type of a requirement, then what happens is that we don't want to build certain test bench components again and again and again, right? If I need a memory model, let's say to verify something, and if multiple IPs need a memory model, then why does every IP team need to create a memory model, right? So as well, they can borrow one from one, the team that has created and reuse it. So you have these two types of reuse requirements, that you have built some IP level test bench components, and you have horizontal reuse possibilities. Build something in the context of UART. I want to use part of it for, let's say, I2C. I want to use it for a simple SPI. I want to use it for USB, Ethernet, PCIe, so on and so forth, right? All horizontal I want to reuse. And this is not just words, right? Like for even in our own simple the course that we are going to do, like APB, for example, right? We are going to do more detailed deep down into the APB. So APB, even simple APB interface, now all these small simple IPs like I2C, SPI, they, and even to an extent like a simple USB control, they are all going to use APB, right? So now I have built an APB verification test bench components, and I can give it to all these IPs, right? So let's say we are doing a UR test bench and we build APB related verification components. We can give them away to all the other test benches. That is one thing, that's the horizontal reuse. And the second reuse is vertical reuse, wherein I built something at my IP level, and if at the subsystem level, wherein I'm putting it few IPs together, like let's say I'm putting all low speed IOs together, right? Like UART, SPI, I2C, or low speed. Then I'm putting all high speed IPs together. Let's say I have USB, I have PCIe, I have Ethernet, they are very high speed, so I'm putting them together as another cluster. And when I'm trying to verify these are two different, like a low speed IO cluster, a high speed IO cluster, I can reuse something that has already been built at the unit level. Not everything, but some parts of it I can reuse it at the subsystem level. And then these subsystem will be put together. So I'm going to put in low speed IO, high speed IO, bunch of memory controllers, and then maybe my own some secret sauce processing engine plus ARM or some RISC-V processor, and build a SOC out of it, right? So now there also, like for example, my UART interface externally, I still have to interface it with some UART bus functional model. So I can reuse that model from the unit level. So I need a way that I can reuse something horizontally and reuse something at the vertically, right? Now when you want to do that, right, so you want to make sure that you have to build certain practices in order to make the reuse more effective, right? For example, when I'm building an UART test bench components, if I closely tie everything to my test bench, then it is not really reusable, right? Like for example, in a single file I have put my APB test bench components as well, which I am building on UR test bench. Like for example, if you remember when we built a 4-bit like a 256-bit counter, everything was in a single file. So if I put it in a single file, not useful, right? Let's say one simple thing like I put everything in my directory where all the UR test bench is put together in one directory. Even the APB thing is over there, and if somebody wants to reuse it, simple fact of like picking those files and taking it out becomes hard, right? So it has to be properly segregated at a very simple level, like a directory, to how does it need to get integrated into another test bench. All those things needs to be thought out, right? And then those practices now were done uniquely across different companies, and that again is there is no unique value, right? That why do you want to figure out how to reuse things, how to structure them, and then how that like horizontal and vertical reuse needs to be accomplished? All those aspects, they are not really a unique value addition for that particular chip company, right? So that is what was the standardized way of doing things. And like the additional fact that even when we built the SystemVerilog Testbench, for example, the naming that we had used, like we said driver layer, like a transformation layer, and then we said generation layer, right? So when we said each one of them, those names, we invented it, right? It's not a standardized name. And so when one team talks one particular language to another team, they may not even understand what you are talking about, right? They might have invented some other name. So how do you tell them that, hey, this thing that you are saying is same thing as what we are doing, so you can take it and reuse? So that won't take off, right? So you needed some way that we standardize this whole way of doing things such that we can accomplish the reuse. So we are talking so much about reuse, and the question might come, in our mind, that what really is reuse and is this possible, right? So let's take a look at example from our own FIFO test bench. So I have put snippets of the push monitor, and then I have put, like, let's say push driver. So this is a driver and this is the monitor. And if we look at it, right, so this extern task main and extern task run, right, these two functions are common, right? Now, and then what we are doing is at the environment level, we had some sort of a phase, right? We had build, connect, run, and then sort of report type of a phases, right? So, and in the run phase, all that we were really trying to do was launch these run threads from each of these active components together, right? We were launching the threads so that they can run in parallel. So this is what I am doing. Now, if I look at it, I don't really have to invent this, right? So this is something that I can do it, like this is the same. So this run task is contained in all the components, and this run is calling the main. That concept is same across all the components. If you go look at it, it is same. Now, why does every component need to do it, right? So why does it even need to provide this definition? Or what if, like, one is that why does it need to provide, and what if different people implemented and different people invented different names, right? Then when we want to call the run, it is so hard for me to figure out that whose which components run task name is what, right? So those all becomes a problem. So now what I can do is I can utilize the object oriented concepts, and I can say that every component needs to do things in certain way, right? And then these tasks must be present. So that is something that that is an interface reuse. So every component, that is whenever we say active component that had a thread, must implement these two tasks in the same name, same same declaration prototype they need to implement. That is something that I can accomplish using the, I'm talking about a very simplest, lowest reuse possible. So I can do an interface reuse via a polymorphism. And then this, like, why does somebody has to sit and write this code of just launching the run task, right? To think about it, right? Tomorrow I had one more component, somebody will have to implement the same names, and not only do that, edit the environment file, and then just copy paste this and change the component name, and then again call run. The same thing, right? Is nothing new. So this is something that we can reuse with a simple, inheritance type of a concept. How to do that? Let's look at up in the next few slides. Okay, so what exactly do we want to reuse? So first thing is that we want to make sure that every active component, the component that contains a thread, must implement two functions. It should have main, in which the primary functionality should be implemented, that should be called in the run. So this is the first thing that we want. So every active component to have these two functions so that it is consistent. Second thing we want is, in the environment, when any active component gets instanced, the run task of that particular active component should be launched automatically, right? Like in the previous slide, we saw that the run task of the environment, we were explicitly coding that particular component dot run in the fork join none. We were calling that particular task, right? So we don't want to do that. We want it to automatically happen, that whenever an active component has been instanced, the developer need not again go in the environments run and have to explicitly again call whatever the new component that he has added, that dot run. We don't want that to happen, right? So now this concept itself is nothing but a fundamental methodology, right? So we are enforcing certain way of doing things, and when you enforce something, you need to give some benefit. You can't just enforce things, right? So if you enforce certain rules, there should be some benefit, right? Like for example, we enforce traffic rules, and because of those traffic rules, we all move around safely, right? So like that, when you enforce certain rules, you need to provide certain benefit. So what are we enforcing? We are enforcing that you need to name your functions main and run. You can't name whatever you want, and the benefit that you get, you don't have to again explicitly call the run, it will get automatically called. So this is what is the basis of methodology. Now how do we do it? Let's look at it. So we are creating one base class called a GrowDV object, and then we are saying we have an static property in that. Static meaning that any number of instance of this particular object gets created, this particular property will remain common. So we have GrowDV object queue, right? So and then we are calling the queue name as GrowDV components. Okay, this is what we have done. And then we are creating one GrowDV component, and this is the class which we would like every active component to extend. So what are we putting in this particular class? We are saying GrowDV component extends this particular GrowDV object, and we have the constructor, and we have this local function called create. It could be made local also. Explicitly we can add the qualifier local because we intend to use it within the class itself. And then we have these two public functions which are, if you notice, they are virtual. So we are saying extern virtual task main, extern virtual task run, and these two tasks we are expecting any object that extends GrowDV component to implement. So now we are enforcing, right? So we are putting these virtual functions, and we are saying that if you extend this particular GrowDV component, you must implement these two tasks. Okay, and in the constructor of this particular component, what we are doing, we are calling super.new, and then we are calling this dot create. Okay, so what this dot create does is it will add the instance of the class being created to this particular queue. So that is what we have done. So if I summarize, we have this static queue, and then the GrowDV component is extending the object, and whenever the GrowDV component gets instanced, that particular instance handle gets pushed into this components queue. Okay, that's the first thing we have done. Now this itself is our base classes of our methodology. So we have two base classes in our methodology, and then what we are saying is now any active component that is going to get implemented in the environment must extend GrowDV component. So let's say we re-implement our push driver and we are extending it with the GrowDV component. Now we don't need to really declare main and run, they are available, and you already know the functionality that goes in the main and run. I am not going to show you that because that we have already seen. Okay, so let's say we extend it and then we implement those two functions. Now what is interesting is that then we create the new of the FIFO push driver, and that component's handle gets pushed into this GrowDV component. And then what we have is that we have one more which happens behind the scene. We have something called GrowDV root. Okay, so the GrowDV root is something that's going to get created as soon as the the GrowDV, let's say we package all of these together, then we in the background we create one instance of the GrowDV root. And in the GrowDV root, what we will do is we will call the function run components. Okay, that we will do it in the background. For now, don't worry about it. Where do we call it? In the module where we instance the DUT, where we instance the test bench. Let's say in one of the initial blocks we are calling this GrowDV. We are creating one instance of this GrowDV root, and we are calling run components from there. Okay, now when we do that, what happens is that it is also extending from the GrowDV object, so it will have access to this particular queue, and then it will go through each of the instance handle. It will do the casting, because we know that each of these objects, although they are stored in the the base class pointer, but they are holding the extended class instance, right? So we can do the casting, and the casting will be successful. So after casting, we are doing fork join none, and we are launching each of those threads, right? So now, of course, this is not a complete solution. Don't look at it from that point of view. It's just giving you an idea of how methodology does things, right? So now whenever a component gets instanced, I don't have to worry about when I should be calling the run or where I should be calling the run. It will get automatically called, right? So I am able to enforce these two rules, and I am able to call this run. Of course, we have not filled in the space of how exactly this GrowDV route gets utilized and all that additional details, we are not filling it in. Don't worry about it. Just get the idea that you can implement certain base classes and enforce certain implementation, and with that enforced implementation you store some extra information, and that extra information you utilize in the behind the scene to do what is required. So all these aspects you will see in much more sort of a detail in the context of UVM, not exactly that how it does in the background. We will look at it few snippets of how it exactly does, but from the point of view of a user point of view, because that's what we are interested, right? We are not going to develop a UVM, we are going to use the UVM, but in order for us to use it effectively, we need to know a little bit of how things happen so that we get that idea and we don't feel that, oh, like is some sort of a magic. It's not, right? So it's again ultimately a SystemVerilog code, and by enforcing certain things they store some extra information, and that extra information that they store, they utilize it for doing some extra functionality, right? That's the whole the idea behind the set of base classes and set of static classes that we are going to see, which are sort of UVM. There's a UVM root, so this GrowDV root is in fact sort of reflecting that. So we will see some of it in the context of UVM, but this is a sort of a simplified view of it, and once you get a hang of it, you can extend the same to the UVM concepts going forward. So now that we have looked at like what's the basic idea and how the inheritance and polymorphism is utilized and how they sort of enforce set of rules, and with the help of those rules, how do they collect some extra information about what we are doing, either through virtual virtual methods implementation, or through the storing the handle of the objects that we are creating, how those all get utilized. So we got a some idea about it. Now let's sort of confirm that the idea that we have looked at and what exactly exists is sort of in line. I am giving you a flavor of one of the UVM base classes, because since we implemented a component, I just want to show you. So this is the source code. This is a snippet of source code. It's not a complete UVM component source code, but this you can anyway go to the UVM source code, the paths that we had shown it during the introduction. You can download the UVM source code and you can actually look at this particular file. So I'm just showing you a snippet. See, this same thing, right? Virtual class UVM component extends UVM report object. So this is there's some object hierarchy, and then there are bunch of properties and the methods that have been provided, and some methods and properties are utilized internally and some of them are exposed to user for implementation, right? So for example, there is a concept of phasing that will come. We had seen like a basic phasing even when we had built a SystemVerilog Testbench. We had build, connect, run and report type of a phasing that we had seen, the basic phasing. Same thing in much more elaborated form exists even in the UVM. For example, you'll have build phase, you'll have connect phase, start of simulation phase, run phase, then there is a reset, configure, main and shutdown phases. You have extract phase, check phase, report phase, final phase. If you look at it, each one of these are just the virtual tasks, right? And what it means is that any class that extends a UVM component must provide this implementation, and then these tasks and functions, since they are enforcing the name, we will automatically phase them. So the UVM root will automatically phase it so that across all the component it is able to do it in a synchronized form. Okay, we will look into more details about the phasing aspect. Don't worry about it too much. What I want you guys to sort of notice over here is how each of the functionality that it is going to provide, it's predefining some functions and it is predefining some additional properties, and it is utilizing all of them to provide the functionality that it promises, right? So for example, the UVM component, when we look at it in more detail, you will see that it helps you establish a hierarchy within the test bench, right? So because it's an active component that stays throughout the duration of test, it establishes a hierarchy, and those hierarchies are all represented over here. Whatever the parent-child relationship that comes between the UVM based hierarchy, it all gets stored over here. There are additional properties and methods provided which store that information, and that information is what we eventually consume. So if I want to ask, okay, who is the parent of this particular component, I can use get parent to get to know about it, and that parent information is again always passed whenever we use the constructor for this particular component. So that also we will see whenever we call create, which is a factory based way of constructing a particular object. We pass the parent, and that parent information gets stored, and that is what we eventually use it for building the hierarchy. So without worrying too much about the actual details over here, the concept that we need to understand is that we create this bunch of virtual base classes, and we provide bunch of virtual functions that a user must implement when he extends it. That's the rule that is being enforced, and when he adheres to those rules, there are benefits like I can find out the hierarchy. I don't need to worry about having to call the run task parallelly in the environment, right? So when any component that I've extended from the UVM component, the thread for that particular component which is present in your run phase gets automatically launched parallelly. So the UVM will launch a thread for you. You don't have to explicitly launch a thread. And the ordering, for example, the build, connect, run, report, all of them, the ordering will be done by default from UVM. You don't have to do it. You just have to implement what needs to happen in each one of those phases. So as long as you do it, you think of it like an application form. Just fill the application form and rest of it automatically takes place, right? So it is like that. So you fill this information, rest of it, the methodology takes care of it, right? So this is the primary concept that I want you to understand. We saw an example and in a very simplified form, and now you can look at it. The concept remains similar, and we have much more details over here. Don't worry too much about the exact details of this particular class. We will look at it in the future slides. So now that we have gotten a flavor of it, let's just summarize. So what does it really mean to learn UVM? Okay, so 70% of learning UVM is nothing but reading and understanding and using the base class library code which is written by other engineers. So there are some engineers who have contributed to build the base class library, and as the users of this particular base class library, our job is that we will read the documentation, we'll read a bit of base class and then figure out how to use it, right? So this is nothing but, and what I want to sort of emphasize over here is, don't think that, oh, this is some code, right? It is not. It is just a SystemVerilog code. I want you guys to remember it, that since you know SystemVerilog, at any point of time you can open a SystemVerilog base class and look at it. Okay, it's just a SystemVerilog code. So all that you are doing is somebody has written some code and has given it to you, and now you can extend some of those classes, put in your functionality, and then there is some built-in things that will happen that will implement what you have understood, right? So through the documentation, it's going to explain what functionality a particular class is going to provide and what you need to do for that particular functionality to become complete for your design. Okay, that is what you will do it, and once you do it, the specified functionality of that particular class will be delivered. So this is what it is. So you need to read the documentation, and you need to develop the sort of habit of reading UVM base class in doubt, because sometimes only reading the documentation may not be like, it may not make it very clear. So don't be afraid to get into the base class that you intend to use and look at it a little bit. You don't need to get into the full depths of it, but few things, if you are not very clear, don't be afraid to look at it, because it's just a SystemVerilog code. And so 70% of it is that you will just understand these are the different base classes, these are the various methods, and which of them are virtual, which of them are non-virtual, how do you call them, what functionality you are supposed to implement in each of those virtual functions. This is what is 70% of UVM. It's understanding some code, some SystemVerilog code that has been written by others. That is 70%. And the 30% of it is some core concepts, right? So the core concepts that bind all these base classes. So the good thing about UVM is that somebody could have said only 30% core concepts and left other to implement the way they want, right? But they have not done that. So they have specified some concepts and made those concepts concrete by providing base classes, so that there is a guideline in the form of executable code. It is not just a verbal thing that they are saying. They are providing you the guideline in the form of an executable code, so that whatever the guidelines that are recommended through the core concepts becomes reality. So you extend each of those core base classes. Then you with your background of core concept understanding, you implement the required functionality for your design in each of those functions, like filling up an application form, right? So you fill up those application forms. In the application forms, you would have seen that you have few fixed fields and you have few variable fields, right? I could have name, address, phone number, and so on and so forth. So each of those virtual functions are your name, address, mobile function, and what should be filled up is your individual information. So you fill up a form and then you get admission to college, or something more happens, or you get a job, right? And then your laptop gets issued, your ID gets created, your payroll gets created. All of it happens just because you filled an application form. All that happens in the background. Same thing is in with UVM. Various base classes are the actual interface, but within that there is a lot of things happening behind the scene, right? You just fill those forms and then processing happens behind the scene to make everything happen. Okay. So from this point onwards, you have to understand one thing, that reading, and we often ignore this point, right? We always think that we are going to write a lot of code, right? In industry, that's not what really happens, because there is enough legacy, right? So the industry has written a lot of code. So reading and understanding to the extent required, this is very important. We can't read and understand each and every line of the code. The UVM itself, as we have seen, it is more than 70,000 lines of code, more than 300 base classes. So there's no way we can read everything and understand. I am not saying that you should. I mean, of course, if you are interested, you can do it, but it's not mandatory. Okay, so the key thing that we need is we need to learn to the extent that is required, because it's an ocean. There is so many things. So you learn what you really need to get your job done, right? So then being able to use the code written by others. So we always feel comfortable with the code that we have written, but what we need to develop is the ability to become comfortable with the code written by others. And this is an extremely important skill. I can't emphasize how important it is. You should be reading more and more the code written by others to understand how various patterns get used in the code written by others. And this is the main skill that you need to start building from now on. This is the main industry skill, that you look at the other people's code and being able to understand. And that is what is all the UVM is about, right? That once you learn an UVM test bench, right? Today, once you learn this UVM, in any place you get employed and there is an UVM test bench, the whole thing is going to remain same. That is a good thing about it, right? You don't need to know how that company has done it. You can look at like which are the active components in a particular test bench. If we had done it in our own way, then you would have to like grep for fork and find out which are the components that are forking off the thread and then follow them, right? But now you don't need to worry about it, right? Any base class, any class that's present in their test bench that's extending a UVM component, you know that it's an active component. It became very clear, right? So anywhere you go, in any company you go, if they say we have a UVM test bench, then using these concepts, you can understand the overall how the test bench has been structured, because you know each of these components, right? So that is the benefit that you gain, right? It makes the ability to read and understand the other people's code easier, and we should practice this skill more and more. So the same thing you should do it with eventually after we do the bootstrapping, you need to start looking at the UVM test bench for the UART UVM test bench that we are going to provide. You should start looking at it and start understanding, and after doing that, you should start exploring the other test benches available in the GitHub links provided by different people. Okay, this is the overall scope of what we are going to learn in UVM, categorized into few categories so that it's easy for us to remember. So the top level is where we generate various stimulus. So sequence item, you can think of it like equivalent to our FIFO transaction. Sequence is equivalent to where we were putting a loop and generating series of random push and pops. Then there's a concept of virtual sequences. So what happens is that if you want to run sequences on multiple physical interfaces at the same time, then you use the virtual sequences. That's like, think of it like if I want to run push and pop together, right? So then you use the virtual sequences, which will create the parallel traffic. And then the second level is all your test bench components. So agents are something where it consists of like a sequencer, on which like sequencer is kind of in a way equivalent to your generator on which you run these sequences. So that sequencer will now generate a series of sequence items, and those will be sent to like a driver. So agent will also contain a driver, and it will drive the interface, and it will also contain a monitor. So an agent is a combination of sequencer, driver, and a monitor. We'll see in more detail, just giving you a flavor of it. Then you can build independent components if you want to build an independent checker, or even if you want to build some sort of a transformation logic, you can put all of that in the components. Then there's a concept of subscribers, which we will see. These are used for building your coverage monitors, right? So if you want to build a coverage model, you typically build it in the subscribers. So the name subscribe is indicative of the fact it subscribes to various transactions from different components and consumes it to produce functional coverage. Okay, can be used for doing something else also, but the basic idea is that it can subscribe to different test bench components and take those transactions and do something with it. Then you have these scoreboards. There are some base classes that can help you ease the process of building scoreboards. And then we have environment class. Like if you remember, we had doing a lot of sort of build, connect, and then run, finish. So we had those set of a series of tasks that we had defined within the environment. So same thing, this will standardize and provide it further. So there's an environment based class for that. And then end we have the tests. So the basic idea is the environment will instance all these guys. So it will instance agents, components, subscribers, scoreboards, and then tests will instance environments, configure them, and run some series of sequences on the agents present within the environment. That's the basic idea. Okay, and then there is a third layer wherein all the test bench components that we have created, agents, components, subscribers, scoreboards, all of them now need to interact with each other, right? So there is something called transaction level modeling. These provides the ways for these components to communicate with each other. So like we had the mailbox, so in a way it's sort of advanced mailbox type of a concept using the TLM is implemented. And then if you have some classes or interfaces that we need to pass around, we were passing it through the constructor, but that sort of ties it down, right? So now whenever we instance, we need to pass it, so the flexibility reduces. So then there are set of these databases which are global in nature, through which you can put something in the database and some other component can take something out of that particular database, right? So there are these config and resource DBs. There's a concept of factory. If you remember, in our 5.4 test bench, we are overriding the config to create a different set of transactions. So in the UVM, that concept is standardized with the help of factory. So you can override a particular object using factory. As a concept of objection, wherein test can say that okay, when the test should end, right? So when the test should end is controlled by an objection mechanism. And then there is a phasing, right? So phasing is, as we talked about, like you can do when the test bench component needs to be built, when it needs to be connected, when do we run the test, and how do we end the test, how do we report it. All that are defined as different set of phases. So then there's a phasing concept. This is the third thing that kind of glues all of these components that we have defined as a test bench environment. Apart from that, there is a lot of utility classes that these guys can use. There's a reporting utility classes which is made up of set of macros. So let's say you want to log some messages within the test bench, then you can log it with a different level of verbosity control. Some messages that should appear all the time, some messages that should appear only when I enable certain type of options. Like that you can configure using reporting. And then there is a concept called RAL wherein whatever the registers that are contained within the design, you can model them using the RAL. There are more utility classes, but these are the core utility classes, and this is the core set of base classes that you can utilize to build the test bench. In summary, you have a sequences, different types, which is your primary stimulus generation mechanisms. Then you have agents, components, subscribers, scoreboards, which are the primary thing that will implement all the functionalities of your generator. Then the middle functional or transformation layer, drivers, the three layers that we had talked about in the SystemVerilog test bench architecture, those all will be done by these guys. Okay, and then all these guys are instanced within the environment, and then the environment is instanced within the test. And then you have this bunch of gluing options. Through the TLM, you connect these components, and through the config and resource DBs, they can exchange some other information, which is if you are generating transactions, you want to exchange it through TLM. But if you have some object that you want to exchange, like for example, we used to pass FIFO config to all the other components, that you can pass it through these DBs. Okay, and then you have factory for doing the override. Override is what allows the test to override various things so that it can configure the environment in a way that it wants. Objection is a mechanism that you control the end of test, and phasing make sure that you are ordering everything in a way that the test execution is well defined. You have utility classes, reporting, and RAL, which help you do it more efficiently. So this is the broad lay of land for the UVM. Okay, so these are some of the the list of core concepts that we need to really understand as a part of the UVM, and we are not going to go in depth in each of these at this point of time, but we briefly introduce them and look at few of them. And but as we go through the entire session, we are going to get into enough details into each one of them. Some of them will individually look at it, and some of them we will look at in the context of bootstrapping that we are going to do. So the first concept is test intent versus environment. So we will look at it a little bit more detail. The idea is that we treat everything like a processor and instruction. Okay, so the idea is that you need to differentiate. You treat the environment as a processor. Okay, and the test is an instruction. So you write, every test is a series of instructions that you are writing, and then the environment is a processor that will execute them. So you write the environment like a programmable engine, and don't put test specific functionality in the environment. So you have series of tests, common functionality to implement all of those tests. You put it in the environment, and the actual test specific sequences that you need to do, you keep it separated. Okay, so this way the whole environment, lot of components and everything becomes reusable, right? So if I tie everything down to the specific design that I'm verifying, as we looked at it, then we cannot reuse it somewhere else, right? So the common functionality is extracted and put it in the environment. Okay, that's the first thing. And then you have the concept of components versus objects, which we have seen a little bit, that components remain throughout the duration of test. They gets created once and they remain throughout the duration of test and perform the intended functionality, whereas objects get created again and again, multiple of them, they get randomized, they get used, and then they get destroyed, right? So then we have this concept of configuration database that will come in the UVM. We'll look at into more details how it gets used. So the primary idea is that if this is a UVM, the configuration database is a global static object that is present within the UVM. You don't have to do anything, it's always present. All that you do is, if you want to pass some information from one component to another component in your UVM test bench hierarchy, you do it through the configuration database, right? So test wants to pass something to environment, environment wants to pass it to the agents, and then agents wants to pass it to their drivers and monitors. Hierarchically the information flows down, and that information flowing down happens through the configuration database. It's a global object that's accessible to everyone. They don't have to instance anything. Just because they are extending the base classes, it's already available to them. So they utilize this configuration. They're extending, plus they are importing the UVM package. So this whole thing is taken care, it's available. So you can just put something into that global object, and then anywhere in the hierarchy you want to take that out, you can take that out. And you can also specify the whom it should reach, and only that particular component in the hierarchy will be able to take out the information that you are sending. So that is the configuration database, is your global communication channel across the test bench hierarchy. Okay, then there are phases. So as we have looked at it, there is like in our FIFO test bench also we had looked at it, we have this way of building, connecting, running, and then reporting, right? So how do you synchronize all these particular steps is done through the phases. So we will look into it. We'll look into it multiple times, but we look at it to a different level. Now we are looking at it like to the level of just defining it. Then we will look slightly one more level detail in this session itself, and then we'll have one special session. We'll go deep into the phases itself. So that's 3 levels we will do it. So first we are just defining that the synchronization of execution is done with the help of the phases. Okay, and then there is a concept of factory. So factory is an important concept. So in factory, what happens is that you have implemented certain component or you have implemented certain test sequence and you want to override it, right? So you want to override that particular thing. Like you might have implemented one version of component and another version of component has come in, and now without having to go and change the actual environment code, you're not going to change that code. Without changing that code, you can change the object type that gets instanced. Okay, that's the concept of factory. So we will look into it, and in order to do that, multiple things. Again, every facility, you have to remember this, it comes with rules. So the rule of using factory is that you cannot do new of the components in the UVM. You have to use a UVM provided function called create. Okay, only when you use create you can use the factory, and then you have to do some registrations of the components in order to be able to use the factory. So this way, same idea that you have to follow certain rules, and because you follow those rules you get some additional flexibility. So in this case, the flexibility is without you having to go and change the environment code, you can replace one component with a different component, and that's a very good thing in my view, right? That you can change the test bench hierarchy without changing the core test bench code. So that is the functionality that is provided by the factory. And then you have modeling transactions. So how to model in the FIFO transaction and all that, we had done a very basic modeling, like how exactly to print a transaction, how to implement the deep copy, how to implement compare. Like if I have two transactions, how do I implement the comparison function? There is also a transaction recording that is provided, and there's a concept of packing and unpacking a particular transaction, wherein if I'm transmitting them in some protocol format, I need to arrange the fields in certain order. So how do I do that with respect to transaction? All that is standardized, and we will talk about it in the context of modeling the transactions. We'll have a separate session for it. It's an important part. And then comes another important concept called TLM, right? So this transaction modeling for communication, very high level, loosely if I correlate, think of it like a mailbox, right? So now two components have to communicate with each other certain set of transactions, right? So we had configuration database to send some one-time information to configure it, right? Like I want to configure a particular agent to something, you send that information through configuration database. But if I want to send a series of transactions from generator to my driver, then you use the TLM. So TLM at a very high level, very loosely, just to help you understand the concept, is like a mailbox, but much more advanced than the mailbox. And for example, in the mailbox, we were not able to solve one-to-many type of a connection. We had to create multiple mailboxes in order to do that. But whereas in TLM, there already exists a way that you can do one-to-many implementation. So we'll look at it. This is another topic that will go deep. And then you have a concept of sequence and sequencer. So sequence generates a set of transactions, and then sequencer arbitrates among the sequences that are running and then passes it on to a driver. So this is also another key concept. We'll look into it more detail, but just understand that a sequence is where you generate series of transactions, and then sequencer is where it gets arbitrated and sent to the driver, and the test invokes set of sequences to implement its test intent. Okay, so this is the basic concept. And then last is some shortcut macros. So in UVM, what happens, you will end up calling set of predefined functions in certain order that is defined, and once you understand that, by doing it manually, you call them few times, then what they have done is, in the UVM itself, they have provided certain macros that sort of reduce the effort of having to manually code it. So certain sequences are created as macros. So instead of you having to call 3 or 4 functions manually one after, like I want to do some randomization, then in a sequence I want to randomize a sequence item, then send it to the sequencer for the arbitration. Let's say there are 2 to 3 steps involved in doing that. I can use one macro and it will be able to do that. So this concept of shortcut macros will be there. We will not look at it in a very early on stages. We would like you to do by calling individual functions so that you get a grip on it, and once you become comfortable, this is just a productivity boost, right? You can do it by this way also. It's just a productivity boost, that instead of writing 2 to 3 lines of code, you just call one macro, and it will, anyway, macros, as you know, it just results in the text replacement. So we will look at it, and that whatever the tick UVM macros.svh file that we include. So if you remember, we import a UVM package and then we do tick include, those contains these macros. Okay, so this is like a very quick introduction to the core concepts that we are going to learn in the subsequent sessions at various level of detail. In this session we will look little bit more, one more level detail of these, some of the few concepts over here, but in the later sessions we will go deep into each one of these. So imagine that there was no clear-cut methodology possible with the Verilog, for example, right? So methodology has become possible only with the SystemVerilog, and that is because the SystemVerilog as a language provides the right set of capabilities, right? And then what that also means is that any language which can provide equivalent capabilities, then methodologies, as we talked about, is nothing but set of rules, right? So those rules, if these capabilities are present, can be implemented with the any language. Like for example, now UVM is also being implemented with the Python, right? So any language that provides the right set of capabilities facilitates the implementations of rules. So what does SystemVerilog provide? The packages are used, right? So we import UVM as a package, we have seen it, and then that package is delivered as a pre-compiled library in the simulators, so that we can load it very quick. Otherwise, if we had to compile so many base classes, it would have taken a very long time, right? So this is very important component of it, that we package it, and we package it in the pre-compiled format. It's a SystemVerilog package that is pre-compiled. And then there is macros, the tick defines, which are with the, it supports the tick define with arguments which aid in some level of code generation. We will see with some examples, that is basically your multiple line code can be replaced with the single line macro. And then you have the parameterized classes, similar to parameterized module, you can do parameterized classes. And because of the parameterization, it's not just about like address width or data width, but with the type also can be parameterized, right? If you remember, even in our SystemVerilog class session, towards the end, we had seen an example where class was parameterized with a type, right? The type of the object that it processed, or the type of objects which it internally utilized, it can be parameterized as a type argument through which you can parameterize. So you can parameterize a class for a user defined data types, which forms the core basis for implementing the base classes, and yet being able to extend them and implement the user defined functionality. And then like a scope resolution operator for static code, for global utility type of functionality, configuration database, for example, is all implemented through the static functionality, which can be, you don't have to instance the config db, for example, it's always present. Just call it using the scope resolution operator. Then these abstract classes and virtual methods to build reusable standard interface. Like for example, we saw that UVM component, just the class definition of it was a virtual class containing series of virtual functions that can be, that enforce that they have to extend it, and then once it is extended, those must be implemented, right? So that we could see. And then there is a sense of like a polymorphism and inheritance that's present, inherent in the SystemVerilog, and which has enabled both the functional as well as interface reuse. So we will see that in the object base class hierarchy, there is several level of hierarchy of extension, and at each hierarchy provides some unique functionality, right? Builds on what has been already provided and adds some unique functionality, and then depending on what functionality you are implementing, you extend the base class at the appropriate hierarchy, right? And that's all possible because of this concepts of polymorphism and inheritance. And then there is also some level of DPI that is used within the UVM, which provides like some string based regular expression matching, and then the HDL access. This is all possible through the DPIs. So this way, overall, it uses these capabilities of language to implement the methodology. Okay, so as a part of this session, we have laid the context to build further on the UVM, and we have reflected on our experiences of doing verification as to how we did it in Verilog, and then what are some of the challenges we faced, and then how we enhanced those in the SystemVerilog, and we built the coverage driven constraint random verification, and then we understood that how we needed those test benches to be reusable both in the horizontal as well as a vertical reuse model. And in order to reuse those, what do we need, right? And we saw a very basic example. It's not very complete, but we saw a basic idea of what does a reuse mean, right? And then how we can do various things once we enforce certain rules. Using those rules, how we can provide the benefits to the test bench developer, right? So we saw that idea, and we understood now what does it mean to learn UVM. 70% of it is basically understanding all the base classes that are provided and what type of rules that are laid to implement those base classes. And we looked at those three categories of the base classes of transaction, and then the transactor, which is based on the components, and rest of the utility base classes. And then we have also looked at like what are some of the SystemVerilog features that are utilized, and a very brief idea about like a one-liner about each of the core concepts. So this is providing this, giving you a context, because UVM, as we started off, it has had a long evolution. So with this context now, you are set to go one level deep into each of these core concepts, which will do as a part of the core concepts introduction part 2. So in the next part, we will go deep into each of these ideas that we, especially the ones that we discussed towards the end of this session. We will expand one level further on those, and then after the part 2, we will do the bootstrapping, wherein we'll look at one real example. After doing real example, we will do further deep dive into each of these core concepts independent of UART, right? So how this overall thing, each of these areas work in much more detail. So, and then that would be the conclusion for the overall UVM learning. And thank you for listening.